Happy Thursday, everybody. Homework 8 is due right now. If you haven't picked up your homework 7, it's hanging out over there. I have not posted homework 9, but that'll happen, and we'll leave 4 homeworks, 9, 10, 11, 12, left in the semester. I don't know if I've mentioned this, but I'm going to drop your lowest homework assignment if you're an undergrad, and that will not be the 12th one, though. So if homeworks 1 through 11, the lowest grade you get will disappear. Yeah.
Is the reason that it's not the 12th one just so people do the 12th one?
Totally.
Okay.
How could you tell?
I was just curious if
Yeah.
there's anything else special about it.
Yeah, I mean, I do this sort of thing in all the classes. I drop the lowest homework assignment because stuff happens, and I understand that. But most people then decide to just not do the last one. So there's a big hole in the stuff you learned. So you could skip the 11th. Feel free. It will be covered on the final. Yeah, it's an arms race, Andy. It's an arms race. Between you and me, psychological battles are taking place. Yeah. Yes. The final will be like the midterm in sort of format. Yeah, take home. Yeah, you'll have time. Probably too much time. Yeah. Yeah, I think. Well, it'll depend on the sequencing of the day of the final exam. So ideally, you'd be turning it in during the final exam period. And I would give you maybe a week or so before that to work on it. I can't remember how that all goes down, but like maybe the last day of class when we're doing our fun experiment, which by the way will be in VOTI 114A, which is a room I went to check out yesterday. Some of you probably know this room, but it's a room we can make a big mess in, which is the plan. So our last class is going to meet there, and maybe that day you'll get the exam, and you would have a week to work on it or so. I will give you more information about that. Okay, we're finishing this discussion of dimension. I don't know if we'll exactly finish it today, but we're getting through this idea of dimension. And somebody asked the so what question, like why do we care what the dimension is? And I'm gonna try and start class today with an answer to that question. And then the rest of the class we're going to be trying to figure out exactly how you calculate Lyapunov exponents, which are things we'll need for our dimension estimate, our final dimension estimate. So, okay, so this was the picture I was trying to show you when we had our tech problem last week, or 2 days ago. So this is the Skinny Baker map. Stretching and folding is happening in lots of things we're doing from here on out. Higher dimensions, positive Lyapunov exponent, negative Lyapunov exponent. That's one direction of stretching and one direction of folding. Lots of mixing. The cool thing that Sven tweeted about with where you can just put your cursor down and drag around a fluid. You see lots of stretching and folding happening. There's a tweet about that. If you don't know what I'm talking about, it's really cool. Can't do it on your phone. You need to use a computer. He's making an app. It's not ready yet. Probably looking for people to pay him. Not everything on the internet is free, apparently. So Skinny Baker map, the concept here, you were thinking about this on your homework. You have this direction in which things are being compressed by a factor of 3, and a direction in which they're being stretched by a factor of 2. So one of those is bigger than the other, right? The compression is happening faster. That sort of thing matters when we decide if there's going to be area left at the end when we're done. In this case, there isn't. The stretching is happening faster than the shrinking, or slower than the shrinking, and we end up with a Cantor set, k infinity of x coordinates, along with vertical stripes of unit intervals. And when you do the dimension calculation, the box counting dimension or other ones that we'll learn, we end up with the dimension 1 for the y-axis plus the ln of 2 over ln of 3 from the x-axis. Okay, so that's a number. What does it mean? Does it mean to identify a point in the Skinny Baker map invariant set we need less than 2 degrees of freedom? Yeah, that's what it means. But in practice, like, why does that matter? That's the question I'm going to try and answer. So I'm going to do it by going back to our weather prediction example that we talk about a fair amount. So first day of class, I described why the weather prediction problem is hard and interesting. So you have observations of the Earth's atmosphere. They get combined with old forecasts to get the best possible estimate of the Earth and its state on a grid. And the grid, if we think about different locations and variables that we want, this is a big collection of numbers. It's like 10 billion numbers that you need to estimate to start a forecast of the Earth's atmosphere. Cool. So because we know that chaos is a problem and the model isn't perfect and there are these things that contribute sources of error to our forecast, we don't just make one forecast, right? We don't take just our best guess for what these things are and say, what does the computer say those will be like? We perturb it a little bit in different ways, and then the spread of those perturbations tells us where our uncertainty is greater or smaller. So, for example, I could go to the deserts of the Earth and perturb the humidity in my weather forecast for what the weather will be like next week everywhere on the globe. All of my forecasts, let's say I did that 20 times, I had 20 different forecasts where the humidity in the deserts were all different all over the Earth. What do you think the outcome of all my forecasts is going to be a week later? Do you think they're going to converge on each other? Do you think they'll diverge dramatically? What do you think? Diverge, okay, that's one answer. Yeah, so the whole concept of this class is you make a little perturbation, and it can grow really quickly, provided it's in a direction in which uncertainty grows. What happens in the desert? What's the weather like in the desert? Yeah, it's dry. It's cold during the night. It's warm during the day. There's no humidity. And very quickly, all of these different versions of the Earth that I'm proposing we make a forecast with will all converge onto, that's hot and dry in the desert during the day. It will, the climatology, if you will, of the atmosphere will just absorb those perturbations in the desert. And all of that uncertainty will collapse. And those are negatively Lyapunov exponents if we think about what these different dimensions are, saying, things, that's compression. Things become more and more alike with those perturbations. Okay. What if instead I took my 20 perturbations to be like the locations of high and low pressure ridges between big synoptic weather systems, which steer the atmosphere and what type of weather we get, whether it rains or... What if I perturbed those things? I made 20 different versions of the Earth where those were in slightly different locations or had slightly different strengths. Okay. What do you think happens then? Diverge, yeah. They move apart from each other because that's a particularly sensitive... the atmosphere is particularly sensitive to those types of perturbations. I'm not expecting you would know this. You haven't had classes in meteorology. But, okay, but here's the important thing about dimension and why we're talking about this in the context of doing science. The important thing is, with 10 billion degrees of freedom and an estimate that size, that it takes, hours and hours for supercomputers to run, I don't get to decide, I'm going to make willy-nilly, hundreds of thousands of versions of the Earth and forecast them all forward. I only get to make a few cleverly chosen perturbations of my best guess. I'm going to suggest we don't do it by changing the humidity in the desert because I don't get any information back from that. I'm going to suggest we do it in regions where uncertainty could grow potentially quickly because that's going to tell me the most information about what the future state and the fidelity of my prediction of that future state is going to be. So I need both of those things. Not just what we think it's going to be like, but how likely my prediction is to be correct. Okay, so the dimension of the sort of the local dimension of uncertainty in the atmosphere is a thing we can calculate. This is a picture of it. I'm getting to the picture. We can take what the weather's like here in Vermont or here in New England and perturb it a little bit in an experiment We can do that hundreds of thousands of times on the computer and see what happens. And maybe it matters a lot. Maybe it doesn't matter at all when we make perturbations in the, geographically speaking, in the deserts. And this is a more abstract space, but if there's 10 billion numbers, that's a vector of length 10 billion that identifies the state of the atmosphere. I'm going to perturb that vector with another one with tiny entries of length 10 billion also. Probably most of them are 0. That's a little perturbation of my best guess. We will use linear algebra to do stuff like that because it's in this space. It's important that you know which direction you're perturbing things in. And we're going to choose, let's say, 20 clever perturbations of that best guess. And the process by which those perturbations are chosen is a really important one and depends on the dimension of variability for that state. The fractal dimension is an important concept for this idea that I'm talking about. Because in some regions of the atmosphere, it really doesn't matter what perturbation you make. Things are always the same. Things are always dry in the desert. Okay, so this is a picture that, so when I was in grad school, there was another grad student named DJ Patel who worked in our chaos group on quantifying the rate of expansion of small perturbations of the atmospheric state for various regions of the Earth. And this is a sort of meta map of all of those. So I think that the idea here, I can't remember how many he used, if it was 10 ensemble members or 20. But the concept is here we're measuring the number of those dimensions on average in which the uncertainty grows for different parts of the atmosphere. So if you start with a 20-dimensional state and things are not going to be stretching apart in all directions, there's some folding too that happens. And we're going to quantify today how to measure those in different directions, whether stretching or shrinking is happening. But basically this is saying that stretching happens more often where it's blue. Okay, there's more likely to be stretching where it's blue, which is where most of the energy for the Earth's atmosphere, the sun hits the tropics and puts more energy into them than it does the northern latitudes and the southern latitudes. And so there's more energy and there's more mixing and there's more convection and thunderstorms and all that stuff. And that's basically why we end up with this band of more uncertain behavior happening near the equator. Things grow faster. There's more positively operative exponents near the equator. Yeah?
What if the South Pole have a greater effect than the North Pole?
Yeah, I think that because of, so the Southern Ocean is sort of its own, I don't know the answer, I'll make some things up. The Southern Ocean is its own, lots of storms all the time. There's very little land mass in the Southern Hemisphere compared with the Northern Hemisphere. So if we think about, what's actually happening here is there are perturbations of the atmospheric state over many time periods, like for half the year. Back in 2000. These are hindcasts. You go and do these experiments after they've happened, so you don't have to wait to see what the weather's like. And so, the weather is particularly bad in Antarctica, and it's bad for lots of reasons. One of which is all of the storms that happen in the Southern Ocean, and so that's why I would guess that it's worse than the North Pole, where there's not as much energy coming from the ocean to stir up the atmosphere nearby. So I think it's an energy thing, but I don't know for sure. I'll tweet out this paper. It's only a couple pages that describe what's going on in detail in this picture. But other questions? Okay, so this is, if you're in practice trying to make weather predictions, you have to decide what of these 20, these are 10 billion numbers that define my state. I got to make 20 perturbations of those 10 billion numbers, and those are vectors too. And that's a little ball, an uncertainty ball in the 10 billion dimensions, but it's only 20 that little ball. And the question is, well, which of those directions are going to stretch or shrink? We're going to try and measure that in a, like in a straightforward two-dimensional Henan map. We can understand it. We can write it down and draw circles that become ellipses. But why does it matter? It matters because we use this sort of stuff, this type of mathematics, to decide how to make good forecasts for things like the Earth's atmosphere and then other systems that are important, like space weather, if you're trying to decide whether there's going to be some huge magnetic storm. People at NASA do that. They try and figure out, based on the state of the sun and what sort of energy is coming out, what the flares look like, whether we need to prepare for some big, blackout caused by all that radiation. Questions? Okay. All right, we're going to write some stuff down now, I think. Yeah. All right, and on your homework, you're going to be calculating the Lyapunov exponents of maps in dimensions higher than 1 now. This is going to be pretty much about linear algebra, which makes some of you feel warm and fuzzy. It makes me very happy. Others, I'm sure it's like, get that stuff away from me. But this linear algebra is the most important math you're going to learn in your life. So we're going to talk a little bit more about it today. And this is section 5.2, and it's called numerical calculation of Lyapunov exponents. Okay, so you'll recall that last class I drew, I guess it was in 3 dimensions, but the basic concept was I had some initial, in 2D it would look like this. I have some initial vector v0 whose future state I care about. It gets sent by the map to f of v0 over here, and perturbations of v0, which can be thought of as living in a little ball around it, my uncertainty ball, not so sure what it's nearby here. I want to know what happens to those perturbations. So if v gets sent over here to f by the map, this circle of points around v0 gets sent, if this is nonlinear, it gets sent to some wiggly shape over here around v1. And then what we're going to do is approximate that shape. If it's super nonlinear, it's weird. If this circle gets really small, we can think of this as looking more and more like an ellipse, whose properties I can predict using linear algebra based on the Jacobian matrix evaluated at v0. That's the matrix of partial derivatives of f. So that's the stuff that we're going to quantify today, how to actually do that. And if there's one direction that's stretching and one that's shrinking, I'm going to keep track of that. The axis lengths are things that I can, using eigenvalues and eigenvectors of actually it's J transpose, I'll be able to get the properties of this ellipse. And then this is going to keep happening over and over again, right? And then v1 gets sent somewhere by f to v2. v2 gets sent somewhere by f. And around each of these points, new stuff is happening. The directions are changing. Because f depends on what things are. The Jacobian will, if it's a nonlinear map, will depend on where I am in the state space. So this is going to keep happening. I'll put a little ball around v1. It'll get sent to v2. So here's v2 down here. And so if I put a little ball that ball then gets sent to some other shape down here that's approximated by an ellipse. This is fun. Okay. The difference between the linear and the nonlinear, or the linearized version of the nonlinear map and the nonlinear map, that difference shrinks as this ball shrinks. All right, Taylor series got like higher and higher derivatives, and but as h gets small in that Taylor series, those higher order terms start to get less and less powerful, and it's really just that first term that matters, which is the Jacobian. Any questions about my picture so far? So we're going to be keeping track of this. We're going to try and use two-dimensional things we can draw, but this is the stretching and the folding. The folding is the direction that's shrinking, that the dynamical systems do to the state space on which they act, stretching and folding. In your head, you can think the taffy machine. I got all these states, And a taffy machine is the equations that are going to stretch them and fold them. Stretch and fold. Stretch means uncertainty is growing in that direction, and folding means uncertainty is shrinking. The desert, humidity, that's the shrinking direction. And like the hurricane that's riding some ridge of pressures, that's the stretching, because that's a very, like pendulum standing vertically type of state. Small perturbations have big consequences. Cool. No questions? Okay. Linear algebra. Here we go. So there was a Jacobian matrix at step n of this procedure that we wrote down last time. And so we have this idea of we have a function f that we're iterating n times around some initial condition v0. And I would like to know the Jacobian matrix of that f. And this is typically difficult to write down. For large n. Just like, even for the logistic map, you wouldn't want to write down what G7 is. That would be some horrible polynomial. Then take its derivative, it's Jacobian matrix, lots of algebra there. So we approximate, instead of writing it down exactly, we approximate the ellipsoid, which is just a ellipse in 3 dimensions or more, the ellipsoid J sub n acting on the unit disk U on the computer. To write down an ellipse on a computer, really what you need is the point at the center, and then the axes, which are just vectors in that space. If it's a 2-dimensional ellipse, you just get these 2 vectors leaving the center, and the lengths. And linear algebra will give us those things, the axes, and the lengths. Okay, so Jn, U, this is a matrix that we're not going to calculate, times a circle. U is the unit disk in whatever dimension we're in. So in R2, it's just the unit circle, and it's the unit sphere in R3. So this thing has axes of length R sub k super n. So like here, this is R1 if n is 2, super 2, and this is R1, oh, that's the second dimension, R2, super 2. Those are the lengths of those axes. They're not the directions, but the lengths. This one looks bigger than 1, and that one looks smaller than 1. So as I've drawn it so far, it looks like I'm going to end up with 1 positive Lyapunov exponent and 1 negative 1 for this cartoon on the board. Right. JNU has axes of length R and K. Subscript is which dimension. Superscript N is like how many iterates I've done. Yes, it is how many iterates I've done. Where this R sub K super N squared are the eigenvalues of J plus U, J transpose. So if you didn't learn about singular value decomposition in linear algebra, you're going to hear about it today from me. We can learn things about maps from the eigenvalues of J on its own, but they can be negative, like because points flip back and forth around some point. This matrix, when I effectively this is squaring J, multiplying it by itself. If it weren't a square matrix like M by M matrix J to begin with, this would be a way to make it square, because a matrix times its transpose, you get a square matrix back. It has eigenvalues that are positive or 0. They can't be negative when you take a matrix and multiply it by itself. You get eigenvalues that are positive. So the lengths of these axes have to be 0 or bigger. If one of the eigenvalues of j is 0, one of these axis lengths will be 0. So I take a disk and it becomes a line right away if one of the eigenvalues is 0. One of the dimensions of the ellipse will be 0 in that case. And the determinant would be 0. The volume of the ellipse would be 0. Yeah. OK, and then the eigenvectors of this matrix are going to be these axes. Am I writing that down yet? Not yet, but the eigenvectors that correspond to these. And yeah, the thing on the inside, the r's, these are called the singular values. Their squares are the eigenvalues of this matrix. We'll write all these things down. OK. These can be very hard to find numerically for reasons that I'll explain. So this process, if we do it lots of times, as you'll note from that animation, things get really long and like this ellipse will get super long and thin, and it'll stop looking like an ellipse. It'll turn into some crazy thing, and it becomes very hard to write down numerically these axes when one of the axis lengths is hundreds, thousands, millions of times longer than the other. Numerically, that becomes a difficult thing for the linear algebra to handle. What will end up happening is that this matrix will become closer and closer to singular. Its rows will become closer and closer to linearly dependent on each other. Another way to say that, if you think about the rows of this thing as like, there's two. If it's a 2 by 2, it's an equation of 2 lines, and you're trying to find the intersection of the 2 lines. That's what a 2 by 2 linear system is. Basically, what we do as we iterate this over and over again is the lines are getting closer and closer to parallel. So they still intersect at a point, but when they're really close to parallel, if you get a few digits wrong in some, like the height of one of them, the solution changes a lot. So that's what it means for a matrix to be ill-conditioned, poorly conditioned, close to singular. That will happen if we keep doing this over and over again because the ellipses will get long and thin. So there'll be something we do to deal with that. OK, we use the chain rule. Because Jn is, I would need to know what f is iterated n times. I'd need to take the derivative of that. But rather, it'd be better if I could just take the Jacobian matrix of f at v0 and multiply it by the Jacobian matrix of f at v1, and so on. First derivatives of all the points along the orbit, those matrices, and multiply them all together, as opposed to trying to iterate f n times. OK, so when we use the chain rule, we'll do, what do I have here? I have Jn times u. And I'm going to write that as, so that's this Jacobian of f iterated n times starting at v0 times u. But chain rule acting on this tells me I can just multiply all of the derivatives at points along the orbit for the first iterative f. Let's say we'll go up to n minus 1 times df at vn minus 2 all the way down to df v0, the first point on the orbit, and then times u. So these are matrices. Each of these is a matrix, a Jacobian matrix, with different entries, because as I move around the state space, my Jacobian changes. Linear map, these are all the same. Same in R2. These are 2 by 2 matrices that are going to multiply u. One confusing thing that I'll note here is these r's, I had the dimension as the subscript in R, whereas down here, these v's, these states, the subscript is it's not the dimension, it's the iterate. So that's confusing. I'm just acknowledging it, but hang in there. All right, so maybe we should I'll just say, so yeah, from now on, my superscript will index which iterate I'm at. And the subscript is going to index the direction of decreasing expansion. Ha. That sounds like nonsense. Decreasing expansion. Remember, these directions as they're turning, right, as I go around the map, they're defined by the first direction is the direction in which things are stretching the most. The second direction is going to be, okay, orthogonal to that first one, which direction is stretching the most. And then the third and so on. And so yeah, so that's like the subscripts on these R's, but that's okay. Questions about this? We're going to draw pictures now, I think. It's time for pictures. All right, so we're going to take a unit ball, U, in our space Rm. On the board, all the stuff we're going to do today will be R2 because it's easier to visualize. And we're going to define it by an orthonormal basis. We'll call those W's. W1 hat, W2 hat, up to Wm hat. The hat means length 1, like I hat, J hat, K hat. I have m of them because there are m dimensions. They're all at right angles to each other, so if I dotted a W1 with W2 or W2 with Wm, I get 0 back. And I'm at iterate 0, so that's my superscript. Which iterate am I at? So in R2, it would look like this. So I have, in R2, I just need 2 orthonormal vectors of length 1. That's the normal part. Orthogonal to each other, they're at right angles. I hat and J hat would work. And this is my initial vector V0. And that's how I define the unit ball to start this process. I have an initial condition, V0. That's like what's the state of the atmosphere right now, this 10 billion dimensional number. That's V0. And then I have perturbations of it. I'm saying let's not put them in the, the humid or in the deserts. I'm saying these perturbations should be in interesting directions in that 10 billion dimensional space. We'll just throw it down onto R2 because it's easier to draw than the 10 billion dimensional ball. So this is on the computer. What the computer sees is the initial condition V0. And then these 2 perturbations of it, which then put me on this disk. That's the unit disk. In math, this is an orthonormal basis in Rm. Questions about where we are, what we've started with here? All right, this is a process. Orthonormal basis. That basis is around V0, which is the initial condition that I'm going to try and represent the uncertainty associated with using this ball. I don't measure V0 perfectly. I measure it to be within some neighborhood. So that's what U is representing, is that little neighborhood of my measurement. OK. All right, and next thing. OK, and we're going to compute. We're going to compute Z. We'll say Z1 super 0 with a vector instead of a hat because it's not going to be length 1, that's equal to my Jacobian matrix F evaluated at V0 times, or dotted with, the corresponding W. So you see my W in the picture? I'm going to take this state right here, and I'm going to multiply it by the Jacobian and see what does that Jacobian do to this vector. That's like running the weather model on that state of the atmosphere instead of that one, but the linearized version. So I'm going to get a new vector back, Z. I'm calling it Z. And it's not length 1. This is just a matrix. On the board, it's a 2 by 2 matrix. It's the Jacobian of F evaluated at V0. And I'm just going to dot it with that vector. And it rotates it, stretches it, shrinks it, whatever. OK, and then I'm going to do that not just for W1, but for all of the elements in this set. There'll be 2 of them in my picture. So Z2 super 0 is going to be my Jacobian of F evaluated at V0 times W2. And so on. I'll have lots of these. The last one is ZM. So over here I have V1, which is where F sent V0. And around it, I'm going to have these Z's. So what do I want to say? Let's say that there's a Z right here. And another Z up here. No, I'm not going to draw this yet. Wait. Yeah. So I'm going to put my Z's down. So I got my V0 and my V1 over here, which is F of V0. And I have Z1, which is where my first W was sent by the linearized version of this map. And let's say I have another one up here that's Z20. These are not length 1 anymore, so they're not hats like the W's were. OK. So these ZI are on the surface. They're on the surface of the ellipsoid that is my Jacobian F evaluated at V0 times U. And not necessarily orthogonal. Usually they won't be. So the W's, they're going to get kind of turned towards whatever the dominant eigenvector direction is for this Jacobian. And that turning, so it looks like they've both gotten, these W's have both gotten a little longer, but they've, in this direction, things have kind of shrunk. So I'm getting some ellipse. Questions right now? Yeah, right.
In your example, are you saying that in the direction of Z1 it's shrinking, and in the direction of Z2 it's stretching?
I'm saying it looks like there's some direction sort of along this axis towards which these are both going. So maybe I'll maybe I'll do this so I can draw. So I've got an ellipse on which these two things sit that, whose volume is the determinant of my Jacobian around V0. The vectors W are each sent to these Z's. They're not orthogonal. And I don't know if I answered your question. Do you want to ask it again?
In your unit ball, you have two directions, right?
Yeah.
And in your example, because it's like in the you have an ellipse.
Yep.
So I'm saying that. Are you saying that on one direction it's shrinking?
Yeah, that's what I'm saying. So it looks like the ball is thinner, or the ellipse is thinner in this direction than the original disk, and longer in that direction. And yes, that's intentional. Yeah.
So those Z sub i's aren't what we were talking about, like the arc hands. They're kind of, are they like showing you where those are going?
Good. Yes, they're not the R's. The R's would be like that and this. Those would be the lengths of those axes. The R's are measured on an orthogonal basis, which the Z's are not. Correct. Yep. So this ellipse that I have that is defined by V1 and then these two perturbations, which you'll note are sort of like, what happened to this? Well, it looks like it shrunk a little bit and turned. What happened to this? It looks like it stretched and turned. So those perturbations are going to lead me to be able to calculate what this ellipse is, but they're not the axes themselves yet. Yeah. Other questions? Okay. We're making progress. Okay, to make orthogonal vectors on an ellipsoid with the same volume as this Jacobian df v0 u, we use, you love it, Gram-Schmidt orthogonalization. Raise your hand if you've heard that phrase before. Okay, so in linear algebra, we typically, that's where you encounter this process, but it's a way to take vectors that are all pointing in random directions, and from that set of vectors, machine your way into an orthogonal set that you can then divide by their length and make it orthonormal. So effectively, we're going to figure out from the two z's what the axes are of an ellipse like this. And it won't be this exact ellipse, but because with Gram-Schmidt orthogonalization, the way it works usually is we have to pick a direction to start with, and it'll be one of these z's. And in fact, I think it'll be easier if we relabel these 2 and 1. So imagine that happened. My 1 got stretched more than my 2. That'll just make it easier. Doesn't really matter, but it'll make it easier to look at. So we'll write down what Gram-Schmidt, if you haven't seen it before, we'll write down what it is. There's discussion about it in your book, about the linear algebra here. So here's what happens with Gram-Schmidt. The idea is, so if we just have two vectors and we want to make them orthogonal to each other, we can start by taking this vector, call this A, and call this B. And we want to make a vector C that's orthogonal to A. What I can do is subtract from B anything in the direction of A. So if I take out of B anything in this direction, what I'd be left with is a vector C where this projection, like if I shine a flashlight down on B, its shadow that it casts lands down here, right here, and I subtract out one copy of A from B, and I'll get C back. And A is orthogonal to C. So Gram-Schmidt orthogonalization will say about this set A and B, start with A, subtract things from B that are in the direction A, you're left with C. C is orthogonal to A. You can then divide A and C by their lengths, and you get a unit circle. Let's say A is longer than 1 and C is shorter than 1. When you divide A by its length, it shrinks back to the unit disk. And when you divide C by its length, it stretches. If C is smaller than 1, it stretches it out to the unit disk. And you're left then with vectors that are on the unit disk and orthogonal to each other. So that's what Gram-Schmidt orthogonalization is going to do for us. It does the orthogonal part. It doesn't do the divide by its length part, but we can add that in. So we're going to need another name for them because the z's, they're pointing in weird directions. They're not orthogonal. We'll call these y. So y1 we'll just set to be whatever z was. And I'm going to make my superscript of my y's 1. What is the superscript supposed to? It's supposed to represent which part of the iteration I'm in. So I think to be consistent with the book, I'm going to say we're updating our iterates now. Y2, which is going to be the second, so this is like A. And then this is going to be, Y2 is going to be like C. I'm going to get it by taking out of Z2. I'm going to take out of this vector anything in that direction. And I want to be left with is this piece down here, or something orthogonal to, maybe I'll use a different color now, since we're getting into our linear algebra here. So these two ellipses are going to have the same volume, and this thing is going to be my y2. How do I get y2? I got to take out of z2 anything in the direction of z0. So I start with z2, and I'm going to subtract from it the projection of z2 onto z1, which looks like this. So those are unit vector versions of y. There's two of them. They're unit length because I've divided each of them by their norm. And there's a few different ways to think about how this happens. But basically what's going on here is I'm taking z2, taking this vector here, and I'm removing from it anything in that direction. What I'm going to be left with is actually, it looks like it's a little less than this if I've done my drawing right. So I'll do this a little more carefully again in a minute. But I'll get an ellipse back that is the same volume as the ellipse that we started with, which itself is a linear approximation of what the nonlinear map would have done to the points on the surface of U. Several things going on. And that gives me this y, which is will be an orthogonal set, which I can then divide by their norms to get back a new set W around V1. So there's more of these equations. Like for y3, I'll need to take z3, subtract its projection onto z1, which is y1, subtract its projection onto onto y2, and we do that repeatedly until we end up with a set of vectors y that are orthogonal to each other, and which represent then the axes. These y's are on the axes of this red ellipse. I'll draw a better picture of this in a minute. So the y, we'll call them y sub j super 1. This set are these y's, so we'll call them y, y1, y2, dot, 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 ym. These are orthogonal to each other. And They are the semi-major and minor axes of an ellipse with the same volume as this Jacobian f times u. So if I'm thinking about uncertainty growth around V0, I want to know properties of the ellipse that this disk becomes. Numerically, it's easier for me to not analyze the properties of that ellipse because the z's that I get back are not sitting on the axes of it. So I approximate that ellipse with this red ellipse that has the same volume, so that it has effectively the same properties in the limit that I care about. And I'm going to do this many times, and I'm not quite done yet because I still have this yeah, so I have these y's, and I need to turn them back into w's so I can keep going. Any questions right now on where we are? One thing to remember is that this disk of points under a nonlinear map turns into some amoeba-looking thing, which I'm approximating with this black ellipse by saying, instead of taking all the points on the surface, just give me 2. And instead of seeing where they go, just multiply them by the linearized version of the map F. That gives me this, what's the black ellipse in this picture, or the green one here. And then I approximate that black ellipse with a red one. There's lots of things happening. Questions? Yeah?
I'm confused. I don't know if something was written down.
Yeah.
But should that just be like, can we just say that that's y1 superscript 1 over the norm of y1 superscript 1 squared?
Sure.
Oh, okay.
Yeah, I wrote it down twice because what actually is happening is we're projecting Z2 onto Y1, like project B onto A to get this thing here. And then we want to take whatever that is out of B. So that's where the minus sign comes from. So really we're taking this thing and projecting it onto Y1. Another way to write this is to slide this into the numerator here. This thing times this thing gives me how much of Z2 is in that direction of Y1, like how much of B looks like A. And that's how, if there's a lot, I want to take a lot out. And what direction do I take it out in? That direction. So there's different ways to write this projection and have it make sense. Yes, it's just the same thing twice. Yeah. Yep.
Isn't there a transpose in there somewhere?
Yeah, there is. If I slide this dot product in, it would be Z transpose Y1 if I put this in the numerator. Yeah, so in linear algebra, you often will learn a different version of this where this is in the numerator. And yeah. Other questions? All right, so the important stuff is sitting. We haven't even said what the radii are yet, but can anybody tell me, can you see in the picture in anything on the board, what the Lyapunov exponents are going to be based on? Something about y, yes? What about the y's tells me what these exponents are going to look like, or the axis lengths? Scott?
Y to be the R value. So
R is the length of the y's.
Okay. So the length of the y's is R. R squared is the singular values. And
R is the singular value. R squared are the eigenvalues of this J transpose. So I'm going to jump in. Scott's right. The length of the y's is the Lyapunov exponent. So you see it here, but then I could also take the norm of this thing, and that's this length right here. Norm of y, since y is just z, that's this length here. So that length and that length, those are the things I'm actually going to keep track of, the norms of the y's. Yeah?
Those are the Lyapunov exponents for the red ellipse.
Yep.
Which are and we're not really worrying about the up and of exponents for what the actual shape is,
Because in the limit, they'll be the same thing.
because in the limit they'll be the same thing,
Yeah.
but not as the black ellipse, but as the red ellipse.
No, the limit of the so the black ellipse and the red ellipse will have the same properties in the limit.
Right. Okay. I'll see.
You'll see. Other questions? So, all right, so it's the length of these y's. Cool. So the w's, if I want to get back to the w's, which I started with, I'm going to get back to them, but now their superscripts has changed. So I have the new set w. So w1 hat. This is going to be my y divided by its length, which is sitting in there. And this is the other reason I kept those things as they were. Because when I divide a vector by its length, I get something that's length 1. And w2 is y2 divided by its length. And these denominators, these are the things, and I have lots of these, I have m of them. Those denominators are the things that I keep track of with respect to, you know, what is my uncertainty growing or shrinking in these directions? And it's agnostic to which, you know, to the coordinate system, because these y's are going to be turning. Every iterate, they're going to be in a different direction. But their lengths that we get from this Gram-Schmidt procedure, that tells me what the resulting exponents are going to be. And we'll just do the last one, Wm hat. They get hats because they're length 1 now. This is Ym divided by its length. All right, these are orthonormal vectors. Length 1, orthogonal to each other. And now in the expanding and contracting directions of the map. Or very close to them, around V0. These norms, y sub I, they measure the one-step growth rate in direction I. So this is cool. One cool thing about this is because we are going to be dynamically, our coordinate system for measuring these exponents is dynamic. It's changing every iterate. It means then that because of that adjustment, these w's, so let me say this. What would happen if we didn't do this Gram-Schmidt procedure is these w's would all collapse on the dominant eigenvector direction, and there'd be no uncertainty left. All 20 perturbations of my best guess of the Earth's atmosphere would be all the exact same thing. And I'd get no new information about uncertainty growth in these other areas. Because that's what linear algebra does. It takes a matrix, it multiplies it by a circle, it turns into an ellipse, and the ellipse shrinks and shrinks and shrinks and just starts to get. But we're not allowing that to happen because every time we go through this process, we get an ellipse, we get the y's. So this is y1 now, and this is y2 here. We get those y's. And then we draw, we pull back to the disk and have these new directions, that one and this one, that are orthogonal to each other in the directions that are expanding the fastest or shrinking the slowest. And that will keep happening. We'll always get this orthogonal set. And if we didn't, all the w's would just converge, all the y's would just converge on each other. It'd collapse. I think we need another example picture. So I'm actually going to try and draw a better version of this. See if this will work. That's about to disappear. Okay. Yeah, right. So a few things could happen. You could imagine that we're always, these things are always turning crazily every time, and this churn in which directions are which. But in practice, usually they sort of settle into a pattern that, so as you, with the anon map, for example, as you start iterating back and forth, there's low dimensionality locally. So they'll end up, sort of on either side of that sickle-shaped thing. When they're on one side, they'll point in one direction. When they're on the other side, they'll point in the other, and they'll sort of settle into a pattern there and not turn very much. So I have an example thing here that I'm going to, we'll draw some vectors on here, see if we can understand what the heck's going on. All right, so I said V0 sits at the center. And then this vector here is my W, and this is my W. I'm imagining that I've started out with, so here's U. This is W1, and this is W2 up here. And this is V0, my initial vector. And I think I have the actual matrix here. Yeah, so my Jacobian at V0, so df at V0, for this particular example that I'm working with, this Jacobian is 2, 1, 1, 5/6. And I could get these aspects of these ellipses that I care about using linear algebra on that matrix instead of like drawing pictures, but we'll get to that. But that's so this is the picture we have. Again, the procedure is now missing, but we take these W's and we send them through the map, and V0 becomes V1. So watch this. So now I go around the new V, I land, and I'm around the new V, which would require another picture, but I'm not going to draw it. So I'm around the new V, and I want to get a new set W, which we will in a second. So call these 0 then, because these are the zeros, they're the first version. So V0 gets sent to V1, and my whole coordinate system is just gone with me, and I'm sitting now at V1. And I want to know what happens to the unit disk that was around V0. It comes with me. What shape does it turn into? So I take my W1 and my W2, and I multiply them by this matrix. And they get stretched and rotated, as vectors do by matrices. So I've got these two ellipses here. The dashed one is the dashed one is where they actually land. So those are my Z's. So let's draw those on here. This is Z. That's going to be Z1. So look at I'll write this down. So the dashed ellipse, that's Z1. And this is Z2. I'll tweet out this picture so you don't have to attempt this insanity yourself right now. Those two vectors, Z1 and Z2, that's what happens when I send these two maps. I just multiply the W's by this vector. I get the dashed ellipse. So the dashed ellipse is df at V0 times U. I'm going to approximate that dashed ellipse with the solid one by doing Gram-Schmidt orthogonalization. So my Z1 becomes my Y1. And then my Y1, I take Z2 right here, and I subtract from it anything in the direction of Z1, which there's a lot of it, right? So if I project this down, I land right here. That's what I need to take out of Z2. So when I take that out, what I'm left with is this vector that I'm drawing right now, but I translate it back over to V1. And I get the other axis of the solid ellipse. And that thing is Y2, which I have no room to write. Y2. y1 and y2 are the semi-major and minor axes of the solid ellipse. And the solid ellipse has the same volume as the dashed one. To get a new set W, I divide the y's by their length. And I get now the unit vector W1, 1 hat that sits right here. So there's that vector. And then I go out along this axis up to here. Because when I divide y2 by its length, y2 is like a third. So when I divide it by its length, it goes out to the unit disk. It gets stretched out. And this is W2 with a superscript 1 because I've upgraded. So my new coordinate system, right angle right here, is reflecting the dynamics local to V0. And I get this new circle around V1. And I do the exact same thing again. And then I do it again and again. I do this over and over again, and I'm recording every time I do the divisions I had to do, the norms of the y. Norm of y1 and norm of y2. On average, those things are going to tell me what the Lyapunov, or their exponents will tell me the average of the stretching. Themselves, these lengths will tell me what the Lyapunov number is. So you can imagine if I start with a disk of length, of size 1, and one of my y's is always bigger than 1, that Lyapunov number on average is going to be bigger than 1, and its exponent will be bigger than 0, stretching. And in the other direction, where these directions are changing dynamically as I move around, I'm going to get something that's smaller than 1. So there's a lot of linear algebra on the board here. Questions about this? Live tweet. Okay. That's coming. So when I get to V, so now I have my new W's, W1, 1 and W1, 2. They are here and here. They're sitting around V1. I'm just going to erase everything in the picture and do the same thing again, but instead of using this Jacobian right here, I'm going to plug in V1. And I'll get different numbers. Because the rates of change around V1 will be different than they were around V0. It's a nonlinear map. And so my ellipse, so my axes have turned, and my ellipse will be different. My next Z ellipse, my next Y ellipse, they'll be different. But as I do this over and over again, I end up with an average of what these norms of the Y's are. All right. So I've said it. Let's just write down what's going to happen next. Ooh, fun. Next, we are going to apply this Jacobian around V1, this matrix, to the WI1 hat basis. That's my new set of vectors here. Which gives me a new set of Z's with the superscript 1 instead of 0, which I then use Gram-Schmidt orthogonalization on to get a new set of Y's, superscript 2. And then I divide those Y's by their lengths, which pull me back to the unit disk, new basis W, superscript 2. And I just do this over and over again. W to Z to Y. Trust me, in MATLAB, this is like 2 lines of code because of linear algebra. The unreasonable effectiveness of linear algebra. This seriously is just a couple things. But I'm doing it in gory detail here because it's impossible to look at those 2 lines of code and have any idea what's going on. So this is more of the, like, we'll draw pictures. We got circles becoming ellipses. Everything feels okay, maybe. All right. So I do that, and then I use Gram-Schmidt orthogonalization to turn the z's into orthogonal set y and then divide by length, which I store. This is the thing I actually care about, is the length that I'm dividing by to get the WI2 basis. So this is a loop. And that thing, the WI2, will put it around V2 instead of V1. All right, and then the limit of this process, we get that this ith direction is roughly equal to the product of the norms of the y's. Going back to one vertical bar for the norm there, just to be annoying. Okay, and then the ith largest Lyapunov exponent is the exponent of this thing. The ith largest Lyapunov exponent is 1 over n sum from j equals 1 to n of the natural log of the y sub I super j. We're going to use these to calculate a dimension on Tuesday for the attractor that results from this process. As you might imagine, like it was with Skinny Baker, if you have, in that case, we had one direction shrinking, so we got some sort of non-integer piece that's smaller than 1. And, another direction stretching, we might end up with a shape that's dimensions between 1 and 2. If it were starting in R2 and we have, stretching and folding happening, we could end up with a set that's dimension is between 1 and 2, and it's going to be the algebra of how to calculate that we'll do next time. Questions? This is a lot of linear algebra. On the computer, this is going to be simpler than what we did today. It's going to be, because each of these, I'll explain why. Instead of having this set of vectors W, you just have a matrix W where the columns are the vectors W. It's got a big matrix W that's got it all in there. If we started with the basis I hat, J hat, it would be the identity, 2 by 2 identity, W. And then I take W and I just multiply it by my Jacobian, and that becomes a matrix Z, whose columns are these vectors Z. And then I can just say, hey, MATLAB, do Gram-Schmidt orthogonalization on Z. And it'll just do it, and that gives me the QR decomposition actually is what does that. A matrix Q, whose columns are the Y's, divided by their length, and the R, the entries in R in the QR decomposition on the diagonal, are the norms of those Y's. And that Q just becomes the new W. That's it. So if you just read that, it would be hard to see this picture, but that's what's going to happen.